to characterize a sorting algorithm? There are generally three things you can talk about. You can talk about time complexity. You can talk about whether this is stable. And what is the third thing?
The approach we use, whether it is by comparison or not comparison.
Sure. Yeah, approach is a general thing about the algorithm, but how do you know whether it's a good sorting algorithm or not? So what are the typical properties? So one is time complexity. How efficient is this in terms of time? Is it giving stable sorting or not? And there's a third thing.
So whether it will handle
That
all
space
kind of numbers or
complexity.
not.
Okay, in place. But that
Yes.
is in place.
Sir,
Yes.
sir, are you sharing your screen?
Yes, you can't see that, I suppose.
Oh, no, sir.
Anybody else can see that or?
Yes, sir, we can see that.
Okay, I'll just
Yes, sir, it is.
Yes, sir.
Sir, I can see.
Yeah, I'll reshare that. I think some cannot.
Okay, thank you, sir.
You can see it now.
Yes, sir. Thank you, sir.
So yeah, third thing is in place, whether that is in place or not. Anything else? I guess these three are good enough for a sorting algorithm. And of course, as you said, yes, some of these are comparison based, some of these are not. So can you name a sorting algorithm that is in place?
Quick sort.
Quick sort is in place, yes.
Heap sort.
Heap sort you can do in place.
So insertion sort.
Insertion bubble.
Yeah, all these are in place. Insertion. Something that is not in place.
It's
The merge sort.
Merge
Merge
sort.
sort.
No, sort is not in place.
Radix sort.
Which one?
Radix sort.
Yeah, counting sort and radix sort are not. Similarly, we talked about stable sorting, like counting, so the quick sort is not. But these are specifically stable. So, and complexity also we discussed. So like that, you can characterize a sorting algorithm. Time complexity, stable sorting, and in place. And we discussed these two mainly, and I just give an idea about bucket sort without going into too much detail, but this is expected order n. And these are actually worst case order n. But they have their own conditions when they can be applied. So this is what we were doing last week. Okay. Okay, so let me ask you a question then. So suppose, so you are given an array of n elements. Let's say they're distinct elements. What is the lower bound on constructing a binary search tree from here? It's a time, lower bound on time. Can you answer this question now? Let's say just think
So
whatever the
omega n?
answers. Omega n. Omega n. One answer. Any other answer? Omega n, you mean there is a way to do it in order n time, but you cannot do it better than O(n). That's what you mean by omega n. Okay. Any other answer? So whoever said omega n, please think of an order n algorithm for doing this. Any other answer?
Sir, omega n log n.
Omega n log n. Do we have an L log n algorithm for doing this?
Sir, AVL insertions.
AVL insertions. This will do in N log n. But the question is, yeah, can you not do better than N log n? So that's what you want to show with omega n log n. Oh, this is the best. I cannot do better than N log n. Okay, anybody else? So two answers, omega n log n. I think omega n log n, at least we know we have an order n log n algorithm for creating a BST. Okay, so that looks reasonable, but omega n, do we have an order n algorithm for creating a BST?
So is it just a BST, not any balance?
Just a BST.
Yeah, okay.
No, sir.
Balanced is also a BST, but you have to create a BST, that's all. No, you cannot. You cannot do in order n. But how do you prove that you cannot do better than omega n log n? How to prove that?
Sir, if we can do better than n log n, then we can just do an order n in order traversal and we will get an order n sort.
Okay, very good. So how to prove that? So you can say that, okay, assume you have a better algorithm. Okay. So then you can use this to with time complexity t, and t is better than n log n, right? So t is better than assume there's an algorithm that is better than O(n) log n. Takes less time. Then you can use this algorithm to have a sorting algorithm that takes less than O(n) log n time. And that too in comparison model. How? Yes, input is set of n elements. What will you do? First, run this algorithm. A, suppose algorithm A. So run algo A to get a BST. Then what will you do?
In order traversal.
In order traversal of BST. So if you combine both of these, what is your time complexity? Time complexity is order of A, whatever algorithm it takes time, plus order n, right? And if A is better than n log n, that means, okay, that is will take better than O(n) log n if A takes less time. And that is not even possible. We have proved that because what you're doing are just comparisons in BST. So not possible. So hence you can prove there is no such algorithm. So that means omega n log n is in lower bound. Can't do it in, can't prove order omega n. Can't have omega n. You have to have omega n log n, lower bound. Is that reasoning okay?
Yes, sir.
So this directly comes from this lower bound comparison sort. You can do some proofs like this. Okay. Now today I'll be talking about something interesting, and you have a lot of algorithms to do that. But let's see why we need to study this topic separately. Okay. So we are talking this topic order statistics. What is the meaning of order
Sir,
statistics? Yes.
sir, I have a question.
Mhm.
When we are creating a binary search tree from n different elements, do we have to do it based on comparisons? Can we do it in any other way? Like if we sort it in ON and then what we get is just the in order traversal of that binary search tree. Can we not make one binary search tree from that in order traversal? Like then that will be an ON.
Okay, I don't understand. You have n elements. Okay, what do you want to do?
N elements. We first sort them in ON, not with
How?
comparison,
How?
and then
No, no, no.
with count sort or
But you
with
see,
count sort or
we are
something like
saying
that.
any general and set of n elements. So what you are saying, we will put a restriction because counting sort comes with a restriction. You need to know their
Okay.
range. Their range has to be order and whatever. I mean, you need to know certain things about them. But these are like general elements. They are all
Okay. Okay.
generic elements.
Okay.
Then counting sort, etc., are not applicable.
Okay, sir. Understood.
And if you can sort them in odd n time, then yeah, that's all we were asking, right? So we are saying you cannot sort them in less than n o n time or less than o n log n time.
So can we do the merge sort in place?
Can we do merge sort in place?
So I was thinking of an algorithm, can I say?
Yes.
So sir, first we divide them in two parts. Then when both the arrays are sorted, we find the median. And then like quick sort, we do a partition and then again call the merge sort on both these parts. So just by means it will be 2 times of the previous complexity. So and it
Okay,
is in place.
complexity one might take a hit, yes, but it will still be o n log n, I think.
Yes, but it is becoming in place now.
Yeah. So it's not the actual merge sort is not in place, but what you're saying, we can make some modifications, of course. We can make some modification. Complexity will take a hit. It will maybe increase by some factors. It still remain O and login, but it can, I think you can do that. And actually, the way you said, we will discuss an algorithm like that in this topic. So, yeah.
Sir,
Mhm.
sir, like previously, what if we just store another array instead of just the simply or linked list along with the BST? So apart from search, so all these activities can be done in order and I mean traversal and those stuff.
No, what is the
So,
question you are asking or you are answering?
so that n log n part.
Okay. So what is your what do you finally want to say? We can create a BST in less than OL login.
BST along with a linked list. So searching will be done in BST, but the traversal could be done in the linked list.
But you do all this deletion insertion, they are all done where in both the parts.
That thing. Yes, sir. Got my mistake.
Sure. Okay. No, yeah, so it's the end of algo course. You should think aloud. Yeah, I may be wrong, you may be wrong, but yeah, you should always think aloud. Yeah. So order statistics. Let me tell the problem, and then you think what are the best algorithms you have for doing this. Okay. So what is the problem? Order statistics.
Excuse me.
Yes, yes.
Sir, I have a doubt how the heaps will be in place. Like in heap sort, we take the maximum, right? We take the maximum and put it in another array, and we do that repeatedly. So
towards the end, I talked about two ways of doing heap sort. Okay. I said, okay, you have a heap. So actually, doing it where you do not have to do in place is very, very easy. You create a new array and keep on putting the elements there, right? But suppose you want to do it in place, I was just saying you can do it like that. So you have this the maximum element, okay? And what you do in heap sort, you delete this and put this element here. This is as if you are just copying this key here, copying this key in this node, and then again restore the heap property, and size becomes minus, right? Size is reduced by 1. Now, while you are doing that, can you not just swap these values? You swap these values. So what will happen? The maximum value will come here.
okay, sir, we store two temporary.
And then you keep on. So when you take this here, the maximum second max comes here. So if you do like that, you will get the reverse. I mean, this is max heap, so you will get in an increasing order. You will get your array in an increasing order. And then if you want a decreasing order, you can just swap the first and last like that towards the end. Yes?
We can change the structure
That
property.
is easy that you know.
Yes.
So that way you can do in place heaps on. That is my understanding. But if you find there's an issue, you can let me know. You can do in place heap sort like this. Okay. Now, let's come to the definition of order statistics. Very simple definition. So it's very similar like search and sorting. Search, very simple definition. You are given n elements and a key, you want to search that. Similarly for sorting, very simple definition. Similarly, what is order statistics? I'll write formally. So the ith order statistics of a set of elements is the ith smallest number, as simple as that. Okay. So that means you are given an elements. Suppose 3, 8, 5, 2, 11, 7. Okay, so n is equal to 6 here. And suppose you want to find out third order statistics of this set. What will be that? The third smallest number.
5.
That's all. That is the definition of order statistics. And you can define it for any order, ith, any general line.
Sir, in this, if we have 3, 3, 8, 5, 2, 11, 7, then will the third order statistic be 5 or 3?
Okay, so instead of 2, we have 3. That's what you are saying.
No, sir. We have 2 3s. I mean, repeated.
Give me the array. So what change you are doing? You're just adding another 3. That's all.
Yes, sir.
So in this case, third order statistics will be 3. So this is the smallest. Then, so you can also think of it as the ith element in the sorted order. If you sort them in an increasing order, so then what is the ith element in the increasing order in the sorted array? So that will also same. So it is also the ith element in the sorted array. So that will be in an increasing order. Very simple definition. Now, which order statistics do you use very often?
First order statistics.
Yes, so very often we use. So very often we use 3 things. 1, minimum. Minimum of this, that is I is equal to 1, first order statistic. Then we use maximum, I is equal to n, that is nth order statistics. What else do we use something? Is the third thing.
Median.
Median. Median is the halfway point. How do you compute median of an array of n elements?
If n is odd, we take the middle, and if n is even, we take average of the middle.
If n is odd, we take you can say n plus 1 by 2 element. Yes, n is odd. If n is even, then what do you take? N by 2, n by 2 plus 1. Take elements. Yes, and you compute their average. And median is a of n by 2 plus a of n by 2 plus 1 divided by 2. That is how you define the median, if depending on whether n is odd or n is even. So these are the 3 things that we use very often, right? So now let me ask a very simple question. Doing this or finding order statistics, does it depend on I? If I have to find ith order statistics, does it depend on I? Whether the depends on the value of I. What do you say?
Sir, if we are simply sorting the array and taking the ith element, then it doesn't depend.
Sorry, yeah, tell me what were you saying?
Sir, if we are simply sorting the array and take the ith element.
Sort the array and take the ith element. What will be the complexity?
The order of sorting.
That is order and log n in Java. Order and log n. So you are saying we have an order and algorithm, order and log n algorithm for doing order statistics for any I. Yes. Very good.
Sir, if we know first I elements, then it will be a order I.
Order I.
If we know the first ith elements.
Sir, if we want to find the minimum element, then it will be order n.
See, I'm talking about general problem. You have n elements given, and you do not know anything about the 10 elements, right? So you have n elements given to you. They are like, they can be arbitrary things. Let's say they are distinct. So in general, we can say they are distinct, okay? Just to simplify things. So assume the elements are distinct. But they are n of those, n elements. Okay, now my question was, you have to find ith order statistics, whether the complexity will depend on the value of I. And one answer I got, if I sort the array and take the ith element, every element, every I, you will have order n log n algorithm. That is good. But in general, what do you know? What do you know? That does it
So we
depend
can do
on-
better.
We can do better, right?
So we can make a minimum heap in O(n) time. And then we can pop I times.
Good. Okay, so I'll come to those algorithms. Sure. So what you're saying, we can do better than O(n) log n for different I, right? For depending on the value of I, we can do better.
Sir,
So,
as we only want
what is the
ith,
best? For which I you can for which I you can do it very fast? Which I you will get the best algorithm?
When I is order 1.
So the minimum and the
Yes. Finding minimum. What is the complexity?
order n.
All right. Okay. You can do it in order n time. How many comparisons are needed for this? How many comparisons do you need?
N minus 1.
At most n minus.
At most. Somebody said n minus 1, somebody said at most. I need an answer. Is it n minus 1 or at most n minus 1?
Always
Yes. Minus
n minus 1.
N minus 1. Okay, what is the algorithm? I think you have used that from PDF's time or even earlier. So you have an array A of n elements, size n. So you want to find the minimum. So how do you start? Minimum is A of 1 or A of 0, whatever way. I'm just starting from 1. Then for j is equal to 2 to n, if aj is less than min equal to aj. That's all. Yeah, that's all. So that's all you use. And you see, you do exactly n minus 1 comparisons. For all, you first initialize the first element as the minimum. For all later n minus 1 elements, you keep on comparing. Is that less than minimum? Is that less than minimum? Is that less than minimum? So, right. The question is, somebody says at most n minus 1. So why can't we do it better? Why can't we solve this problem with less than n minus 1 comparisons? What is your answer?
That minimum element can be located anywhere in the array, so we need to check the whole array.
Right, but why n minus 1 comparisons? Can you take an analogy from something else that you may like? And I'll take an analogy. Why can't this be done? Or if you want, I can give an analogy. Okay, let's think about cricket. Okay, let's think about a cricket tournament. Let's take cricket tournament. Okay. So there are, say, n teams playing. And what you are allowed, you want to find out who is the winner. So minimum maximum is same. So let's say you want to find the winner. You want to find the winner of, to find a winner. There will be a single winner of the tournament. Who will win the tournament? Okay. So what you start doing, you said, okay, what I can do, I can play games between two teams. So what you allowed? So you are allowed to play game between any two teams. Knockout game, just a knockout game. So that means that the game will have a winner and a loser. Somebody will win, somebody will lose. And the one who loses is out of the tournament. Yes. So now think about that. So you have n teams playing. You want to find a single winner. And what you have at your disposal is you can play games. So you play game between two teams, a winner, a loser. Okay. Now think in that analogy, to find a winner, minimum how many games you have to play. Game is like a comparison. So how many minimum games you have to play?
n-1.
Again n-1. Why?
So because each game can knock out at most one player, so we need at least n-1 games to find one player that wins.
Very good, very good. So the reasoning is that, of course, a game gives you a winner loser, but winner is not a winner finally, because the winner has to keep on winning matches with all the teams. But what is important, each game knocks out one team. And for one team to win, n-1 teams have to lose. They have to lose, right? They have to go out of the tournament. Otherwise, they will say, oh, I didn't even lose. So why? How can you make someone else as winner, right? So you have to. So n-1 teams have to lose for one team to win the tournament. And each game can only give you one loser. So that means minimum n-1 games.
Sir, why minimum?
What do you mean?
Means why minimum n-1? Like we cannot have more than n-1 games, but can we?
You can always keep on playing games that are no relevance. I mean,
but once the loser is out of the tournament, how will he play a game?
Yeah, that's a good thing. That's a good thing. That's a good thing that if a person is out of the tournament, how will he play a game? Right.
Yes, sir. Like for every means for every set of players teams, we cannot remove two teams in this tournament.
Yeah. So each game will remove one. So you're saying there will be exactly n-1. Good. There will be exactly n-1 games. If the loser is out, you do not entertain any.
If there is draw, there will be more.
No draw. It's winner or loser. Good. So if you are knocking that person out, yes, there should not be any other game with that person. So exactly n-1 games. Good. So same thing here. So you have to find out a minimum or a maximum. Same thing will apply for maximum. So you need n-1 comparison for finding minimum or finding maximum. All of the n-1 elements have to lose out that, oh, I am smaller than someone. So yeah, I cannot be I cannot contend for being maximum, or I am larger than someone, I cannot contend for being the minimum, right? So that means I need exactly n-1 comparisons for finding out minimum, finding out maximum. Very good. Now let me ask the next question. What if I want to find out the minimum and maximum together? How can I find out minimum and maximum element together? What I mean is that what is the minimum number of comparisons needed? Suppose I'm saying, okay, I can find max in n minus 1, min in n minus 1. So I have a simple naive algorithm now based on my understanding. So what is a simple algorithm? Find min, find max, both independently. How many comparisons?
2n minus 2.
2n minus 2 comparisons. Now question is, can we do better?
Yes, sir.
So, yes, sir.
We can do it in n
We
minus 1 itself.
n beta minus 1.
How will you do better?
So we split the array into two parts, find min and max for both, and then compare them.
Okay, good. So, but yeah, I'm just saying a very simple way. So yeah, it's very similar to what you're saying. So I have an array A of size n, there are n elements. So what I will do, let's say n is even, doesn't matter, but let's say n is even. So let n be even, doesn't matter, but yeah. So then what I can do, divide into set of 2 elements each. So divide the array into n by 2 groups of 2 elements each. Okay. Now let's take an arbitrary group. Say the element, they are a of I and a of I plus 1. A of I and a of I plus 1. Now let's focus on this group and how many comparisons you would have required in the simple algorithm. So you have already have a max and a min computed till now. So for simple algorithm, what will you do? You will compare AI and AI plus 1 with max, also with min. So how many comparisons for this group of 2 elements? 4 comparisons. I need 4 comparisons. But can you do better? Can you reduce the number of comparisons needed?
So we can compare once between AI and AI plus 1, and then we know which is more and which is less.
Compare AI with AI plus 1. One comparison. You know one of them is greater. So suppose AI is larger. Then what we will do? Compare max with AI and compare min with A of I plus 1. Because once you know AI is larger, AI cannot be in the minimum. So no point comparing AI with minimum. Similarly, no point comparing AI plus 1 with maximum because it's already smaller than AI. So that means for these 2 elements you can do with just 3 comparisons. 3 comparisons. Okay. So that means overall you will need, roughly 3n by 2 comparisons. So that is a Bell algorithm. you can find out both max and min in close to 3n/2 comparisons. Is that okay?
But sir, still O of n, so we didn't gain anything.
That's okay. I'm saying number of comparisons. From 2n-2, we got to 3n/2. Here we didn't want, we were not wanting to do it in less than order n. If max is order n, min is order n, how can you do max and min together in less than O(n)? Yes? Do you think you can do that?
Okay, sir. No, sir, we can't do.
No? You can't do it. So, because then you can use that algorithm to find max in less than O(n) time. So we can of course not do it in less than O(n), but number of comparisons could be reduced from 2n-2 to roughly 3n/2. So this is a gain. Okay, this is a gain. Okay. So this was about finding max, min. You can do it in O(n) time. Good. That was I is equal to 1. Now what if we keep on saying, say I is equal to 2? How would you do I is equal to 2? Second order statistics. How would you find the second minimum element?
Sir, we can take the record of the first and second. minimum.
What do you mean?
So we can do first order statistics twice.
We can do first order statistics, okay, then?
And then remove the minimum element again, do the first order statistics. We'll do the first order statistics twice.
Okay. So do the first order statistics. Find first order statistics. Remove from array. And find first order statistics again.
Sir, but remove that again forming, it will become larger.
2n, roughly 2n.
So we can do
Actually,
something like if
2n
AI
minus
less
3.
than mean.
Roughly 2n-3 comparisons, what the way you are doing. So it's, yeah, or I can say 2n, takes 2n time. Yes? Yeah, somebody was saying.
So I was saying you can do something like if AI less than mean, then second mean equals to mean and mean equals to AI. This you might get the second mean.
Like min1 and min2, if AI is less than min1, we check for whether it is less than min2 or not, and we assign.
But even in that case, sir, I think
Most
we'll
cases
get 2n
it's
comparison
most
only.
cases the same.
So, but why are we concerned of this order 2n? Like we never do this, right? We only consider order of n.
Famous order. That's all right. Okay, I just wanted to say that this will take 2n time. This is order n. True. Okay, but I wrote 2 for something important. Because see, you can do, in this way, you can do second order statistics. Now you keep on going for, say, I is equal to k, or I could have written I is equal to I, or just, yeah, say some kth order statistics. If you do in the same way, what is the complexity you will get?
Order kn.
Yes, that is why I wrote k, 2. This will be order kn. Order kn. Yes. Now, you can easily see that this approach looks okay for I is equal to 2, 3 like that. But as soon as you go to general I, because I can be order n easily, I can be order n, and you can even go backwards. You can find, say, I can do it like, okay, if I is equal to n minus 1, I can do it in order 2n. Yes, yeah. And similarly, I can go back. and like this. So it will keep on increasing from here to roughly median. Yeah, at median it will be maximum again. Yeah, it will decrease. But at median this will be really bad. This will be at median. This will be order n square for median. This will be order n square, right? So so okay, this is a simple algorithm, but that's okay if we take I equal to 1, 2, 3, some simple things, and I equal to n minus 1, n minus 2. Like that. This will be fine, but not in general, not in general. So let's say for any k, this will be order kn. Yes, order kn, and for general k, this is not good, not efficient. So what is a better algorithm for any general k?
So create another data structure or something that so that we keep on inserting while actually checking. So for the kth one, I create an array of k elements, and then I take the last one or something like that.
Okay, so what is a better algorithm from whatever you know till now, whatever topics we have covered? So we have an already order and log n algorithm. Yes, in the worst case. Somebody said the first time, you sort them, pick up the kth element. Sort the array, take the kth element. Do we have anything better than O and log?
Sir?
Mm-hmm.
So what if we find the minimum and maximum and then removing both, again minimum and maximum and removing both until we left with only one element, that is the middle element maybe. Can this work? Because we have seen that when we find we'll get 3.
How much time will that take? So the algorithm you're saying will take 3 by 2 times n plus n minus 2 plus up to 0, right?
Yes, sir.
That will be again order n square.
Yeah, no.
So order n log n algorithm, the worst case we have. Do we have a better algorithm? The k can be less than n, it can be less than n, but it still can be something that we cannot ignore.
So someone told about that heap solution.
Okay, let's use a heap solution. So using heaps. Okay. What is the algorithm and what is the complexity?
Order n plus I log n.
Order n
Yes, order n plus I log n.
K log n.
Yes, sir.
Okay, that sounds better. If k is less than n, yes. An algorithm is simple, right? What is the algorithm?
Yes, sir. On to set the heap and log n for deleting. Log n to delete the max.
Removing min k times. You have created min heap and keep removing min k times. So this will be order n plus k log n.
Sir, we can do in order n plus k log k as well.
That was in the assignment that I gave.
Yes, yes.
So you already have a better algorithm. Using heaps itself, you can do this, but you can also do order n plus k log k using heaps. What was that algorithm? Anybody remembers?
Sir, how n plus k log k?
No, I'm just asking you. I gave that in the assignment, and I think I also described how it can be order n plus k log k.
Yes. Sir, we will first make a heap and then we will have a temporary heap. In that we will add the maximum. First step we will add the maximum element. Then we will add its that adjacent. We will add its child to the heap and delete that maximum person, and repeat these steps for k times. Like we
Very
will
good,
add
very
each
good,
time the child.
very good algorithm for doing a lab. Yeah, it's actually very interesting. So algorithm goes like this. So you have a heap. Just take a max heap. We can just generalize that later. Max heap. So where is the first maximum? First maximum is here. Yes. Now, once you know the first maximum, who are the candidates for second maximum?
Sir, it's both
Both its
children.
children.
Yes. So I know second maximum will be from here. One of these. So what I do, I take these two children and put them in a heap. And I find out what is the maximum from there. So that means one I will find out the second maximum, second, the other one will remain. Yes, other one will remain there. Now what is the candidate for the third maximum? Suppose second maximum is this. What is the
So both
candidate?
its children.
What are the candidates for the third maximum?
So both its children and the one that is still in the heap.
3. So now you have 3 candidates, this and the 2 children. So now your heap will have 3 things, you will find the maximum. Again, one of this, suppose now this comes out to be the third maximum. Now the candidate for fourth maximum are this, and its children. If it has children, then. So like that you keep on adding things. And you can see there will be order k. There will be only order k elements in this heap for finding the kth maximum. And every time you have to do operation with k heap, all operations are log k. So yeah, you do order n plus k log k.
So, but how will we remember this?
So that is something that you will have to work out. Yeah, you can do that. You will have to create some nice data structure in which you can
Yes, sir.
elements here and here. Okay, so that you will have to take care, but it's doable. And you can do an order n plus k log k.
Sir, we can also keep a heap of size k and then just ignore elements which make the heap size greater than k, and then find the minimum of that heap.
No, come again. So you're starting from n elements. How are you doing this?
Sir, let's say we keep a heap of size k. Let's say we make a heap out of the first k elements of the n elements, and then we insert elements one by one. But when the array index goes beyond k, we just ignore those elements. And after that, we just find the minimum in the first k elements.
Yes, sir, he's right. This works also.
For finding the kth
Yes, sir.
minimum.
It would be of n minus k log k.
N minus k log k. For finding the kth minimum.
So finding the kth maximum here.
Yeah, kth maximum. Okay, you can do the same thing for kth minimum also. N minus k log k. Is that what you're saying?
Yes, sir. So n minus k log k plus order n, something like that.
No, but if it is order n minus k log k, plus on. This will be, I mean.
Okay, sir, this will be worse than.
Yeah.
Okay, sir. Yes, sir.
So this is still better. N plus k log. But yeah, sure. So using heaps, you can do in order n plus k log k. Anything else? What else you can think of? Can you think of any better algorithm?
So this order of n plus n minus k log k will be better for all values of k greater than n by 2, right? Because then n minus k is smaller. So we can use both of them. If n k is less than n by 2, then we use the k log k and then we switch.
Yeah. Sure. Sure. Better than n by 2. Fine. Agreed. Okay. So yeah. So we have an algorithm that works, say, on n plus k log k, where k is less than n by 2, or now, do we have anything better? No, so that's where we study. So what about the worst case ON algorithm? Will that not be interesting? Worst case ON algorithm for finding out any kth smallest element in the array. Do you think that is possible?
Sir, you mean to say that in worst case it is taking O of n time?
Yeah, for any kth order.
For any kth order. Okay.
I mean, yeah, for any k. Say you find median in order n time, you find fifth largest no n time, you find n by whatever in O(n) time. Will that not be interesting?
Sir, hello. Sir, can we use hash tables or something?
No, hash table you can, but like hash table will give you expected. Hash table will always give you expected O(n) time. But yeah, hash table is not the answer. An answer actually lies into something that you have already studied. So we will use the idea from quicksort. We'll use idea from quicksort but add some more ideas there, and we will make in worst case order and
Search in only one part. We'll search in only one part depending
Yes,
on the
yes.
number of
We
elements.
just write that part and then we break today. So worst case order and time. So let's use a variation from quicksort. So what we do in quicksort? So we have an element array A of n elements. You take X as the pivot, and using the pivot, you transform the array into things that are less than equal to X, and things that are greater than x. And of course, you do quick sort in both the parts. Yes. Here, what we will do, so this is the partition step. This is just the partition step. Now, suppose we do partition. Now, x will come at some position. Suppose this size is n1, this is 1, and this is n2, or you can write n minus n1 minus 1, whatever. Right? So suppose these are the partition sizes. Now, can you write an algorithm for finding kth order statistics? Kth is smallest element. So if k equal to n1 plus 1, so what
Return x
is the answer? Yes. Okay. If k is less than equal to n1 or k is greater than n1 plus 1. If k is less than equal to n1, what will you do? Recursively find kth, the smallest element in the left partition. And if k is greater than n1 plus 1, what will you do? Recursively find
k minus n1 plus 1.
Minus
k minus n1 minus 1 element in the right partition. Right partition. Okay. So, yeah. What is the complexity? What is the complexity?
So n square.
Yeah. So yeah, complexity depends on what are the sizes. So suppose both partitions are roughly equal, n by 2 each. Suppose, then what will be the complexity? Suppose they are n by 2, then what will be the complexity?
order n.
So Tn is T of n by 2 plus O of n.
10.
And this gives you Tn is 1. You're throwing half the elements each time. This will give you O(n) time algorithm. Right? But how will we ensure? But in the worst case partitions can be like n minus 1, 0. Then Tn as T of n minus 1 plus On. And that gives you Tn as order n square. Right? So here is the hint. So can we somehow ensure that the partitions are balanced? So ensure that the partitions are balanced. And they need not be perfectly balanced. Even if they are like 7n by 10, 3n by 10, 9n by 10, n by 10. Do you think that is also fine?
Yes, sir.
That is also fine. That will also work, also works. But they should never go to the worst case. So how do you ensure that the two partitions are balanced is what we will study. So we are meeting tomorrow, 9. Okay. Sure. So any question right now?
Sir,
Yes.
sir, I didn't understand the table.
You didn't understand
The comparison table, sir, with k and n1. Yes, sir. Sir, below. Yes, sir. This one, this table.
So you want to find the kth smallest element. Yes, you apply the quicksort partitioning. So that means these elements are less than or equal to x, then x, greater than x. And you know what is the position of x in the sorted array? That is n1 plus 1.
Yes, sir.
Yes. So if suppose your k was n1 plus 1, then x is
So
the
then
answer.
it will be the answer.
Yes. Otherwise, there are two possibilities. K is less than or equal to n1 or k is greater than n1 plus 1. Two
The
possibilities.
k is less than n1 only.
Mhm.
It can't be equal.
Why not? Because I was checking here n1 plus 1. So then it will be less than or equal to n1 or greater than n
Okay.
plus
Yes,
1.
sir. Yes, sir. Yes, sir.
So then are you following everything else?
Yes, sir.
Sure. So we will continue from here tomorrow then. Okay. Thanks. Bye.
Thank you, sir.
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 Thank you, sir.